Acid dissociation constant. An acid dissociation constant, Ca, also known as acidity constant or acid-ionization constant, is a quantitative measure of the strength of an acid in solution. It is the equilibrium constant for a chemical reaction, known as dissociation in the context of acid-base reactions. The chemical species HA is an acid that dissociates into A, the conjugate base of the acid, and a hydrogen ion, H+. The system is said to be in equilibrium when the concentrations of its components will not change over time, because both forward and backward reactions are occurring at the same rate. The dissociation constant is defined by or, where quantities in square brackets represent the concentrations of the species at equilibrium. Theoretical background. The acid dissociation constant for an acid is a direct consequence of the underlying thermodynamics of the dissociation reaction. The pK value is directly proportional to the standard Gibbs free energy change for the reaction. The value of the pK changes with temperature and can be understood qualitatively based on Le Chatelier's principle. When the reaction is endothermic, Ca increases and pK decreases with increasing temperature. The opposite is true for exothermic reactions. The value of pK also depends on molecular structure of the acid in many ways. For example, Pauling proposed two rules, one for successive pK of polyprotic acids, see polyprotic acids below, and one to estimate the pK of oxyacids based on the number of equals O and OH groups, see factors that affect pK values below. Other structural factors that influence the magnitude of the acid dissociation constant include inductive effects, mesomeric effects, and hydrogen bonding. Hammett-type equations have frequently been applied to the estimation of pK. The quantitative behavior of acids and bases in solution can be understood only if their pK values are known. In particular, the pH of a solution can be predicted when the analytical concentration and pK values of all acids and bases are known. Conversely, it is possible to calculate the equilibrium concentration of the acids and bases in solution when the pH is known. These calculations find application in many different areas of chemistry, biology, medicine, and geology. For example, many compounds used for medication are weak acids or bases, and a knowledge of the pK values together with the octanol water partition coefficient can be used for estimating the extent to which the compound enters the bloodstream. Acid dissociation constants are also essential in aquatic chemistry and chemical oceanography, where the acidity of water plays a fundamental role. In living organisms, acid-base homeostases and enzyme kinetics are dependent on the pK values of the many acids and bases present in the cell and in the body. In chemistry, a knowledge of pK values is necessary for the preparation of buffer solutions, and is also a prerequisite for a quantitative understanding of the interaction between acids or bases and metal ions to form complexes. Experimentally, pK values can be determined by potentiometric pH titration, but for values of pK less than about 2 or more than about 11, spectrophotometric or NMR measurements may be required due to practical difficulties with pH measurements. Definitions. According to Arrhenius's original molecular definition, an acid is a substance that dissociates in aqueous solution, releasing the hydrogen ion H plus a proton, Ha equals a plus H plus. The equilibrium constant for this dissociation reaction is known as a dissociation constant. The liberated proton combines with a water molecule to give a hydronium or oxonium ion H3O plus. Naked protons do not exist in solution, and so Arrhenius later proposed that the dissociation should be written as an acid-base reaction. Ha plus H2O equals a plus H3O plus. Bronsted and Lowry generalized this further to a proton exchange reaction. Acid plus base equals conjugate base plus conjugate acid. The acid loses a proton, leaving a conjugate base. The proton is transferred to the base, creating a conjugate acid. For aqueous solutions of an acid HA, the base is water, the conjugate base is a, and the conjugate acid is the hydronium ion. The Bronsted-Lowry definition applies to other solvents, such as dimethyl sulfoxide. The solvent acts as a base, accepting a proton and forming the conjugate acid SH+. A plus S equals a plus SH+. In solution chemistry, it is common to use H+ as an abbreviation for the solvated hydrogen ion, regardless of the solvent. In aqueous solution, H+ denotes a solvated hydronium ion rather than a proton. The designation of an acid or base as conjugate depends on the context. The conjugate acid BH+ of a base B dissociates according to reading 2. BH++ OH equals B plus H2OH is the reverse of the equilibrium. H2O acid plus B base equals OH conjugate base plus BH plus conjugate acid. The hydroxide ion OH, a well-known base, is here acting as the conjugate base of the acid water. Acids and bases are thus regarded simply as donors and acceptors of protons respectively. A broader definition of acid dissociation includes hydrolysis, in which protons are produced by the splitting of water molecules. For example, boric acid BO83 produces H3O+ as if it were a proton donor, but it has been confirmed by Raman spectroscopy that this is due to the hydrolysis equilibrium. BOH3 plus 2H2O equals BOH4 plus H3O+. Similarly, metal ion hydrolysis causes ions such as LH2O6 to behave as weak acids. LH2O6 plus H2O equals LH2 off of OH2 plus H3O+. According to Lewis's original definition, an acid is a substance that accepts an electron pair to form a coordinate covalent bond. Equilibrium constant, cumulative and stepwise constants, association and dissociation constants, temperature dependence, dimensionality, strong acids and bases. An acid is classified as strong when the concentration of its undissociated species is too low to be measured. Any aqueous acid with a pK value of less than 0 is almost completely deprotonated and is considered a strong acid. All such acids transfer their protons to water and form the solvent, cation species H3O+ in aqueous solutions so that they all have essentially the same acidity, a phenomenon known as solvent leveling. They are said to be fully dissociated in aqueous solution because the amount of undissociated acid in equilibrium with the dissociation products is below the detection limit. Likewise, any aqueous base with an association constant pKb less than about 0, corresponding to pK greater than about 14, is leveled to OH and is considered a strong base. Nitric acid, with a pK value of Ca minus 1.7, behaves as a strong acid in aqueous solutions, with a pH greater than 1. At lower pH values it behaves as a weak acid. pK values for strong acids have been estimated by theoretical means. For example, the pK value of aqueous HCl has been estimated as 9.3. Monoprotic acids, polyprotic acids. A polyprotic acid is a compound which may lose more than one proton. Stepwise dissociation constants are each defined for the loss of a single proton. The constant for dissociation of the first proton may be denoted as cation, and the constants for dissociation of successive protons as cation, etc. Phosphoric acid, H3P offer, is an example of a polyprotic acid as it can lose 3 protons. When the difference between successive pK values is about 4 or more, as in this example, each species may be considered as an acid in its own right. In fact, salts of H2PO4 may be crystallized from solution by adjustment of pH to about 5.5, and salts of HbO4 may be crystallized from solution by adjustment of pH to. The species distribution diagram shows that the concentrations of the two ions are maximum at pH 5.5 and 10. When the difference between successive pK values is less than about 4, there is overlap between the pH range of existence of the species in equilibrium. The smaller the difference, the more the overlap. The case of citric acid is shown at the right. Solutions of citric acid are buffered over the whole range of pH 2.5 to 7.5. According to Pauling's first rule, successive pK values of a given acid increase pKatwo pKon. For oxyacids with more than one ionizable hydrogen on the same atom, the pK values often increase by about 5 units for each proton removed, as in the example of phosphoric acid above. It can be seen in the table above that the second proton is removed from a negatively charged species. Since the proton carries a positive charge, extra work is needed to remove it. That why pKatwo is greater than pKon. pK3 is greater than pKatwo because there is further charge separation. When an exception to Pauling's rule is found, it indicates that a major change in structure is also occurring. In the case of V-Atwo plus Ac, the vanadium is octahedral, 6-coordinate, whereas vanadic acid is tetrahedral, 4-coordinate. This means that 4 particles are released with the first dissociation, but only 2 particles are released with the other dissociations, resulting in a much greater entropy contribution to the standard Gibbs free energy change for the first reaction than for the others. Isoelectric point. For substances in solution, the isoelectric point Pi is defined as the pH at which the sum weighted by charge value of concentrations of positively charged species is equal to the weighted sum of concentrations of negatively charged species. In the case that there is one species of each type, the isoelectric point can be obtained directly from the pK values. Take the example of glycine, defined as AH. There are 2 dissociation equilibria to consider. A plus 2 equals A plus H plus, AHH plus equals cone AH plus 2, plus 2, plus 2. A equals A plus H plus. AH plus equals K2AH. Substitute the expression for AH from the second equation into the first equation. AH plus 2 equals cone K2AH plus 2 at the isoelectric point. The concentration of the positively charged species, AH2 plus, is equal to the concentration of the negatively charged species. So H plus 2 equals cone K2. Therefore, taking cologarithms, the pH is given by P I equals P K 1 plus P K 2 display style mathem Pi equals mathem PK1 plus mathem PK2 Pi values for amino acids are listed at proteinogenic amino acid. When more than 2 charged species are in equilibrium with each other, a full speciation calculation may be needed. Bases and basicity. Amphoteric substances. Water self-ionization. Acidity in non-aqueous solutions. A solvent will be more likely to promote ionization of a dissolved acidic molecule in the following circumstances. It is a protic solvent, capable of forming hydrogen bonds. It has a high donor number, making it a strong Lewis base. It has a high dielectric constant relative permittivity, making it a good solvent. For ionic species, pK values of organic compounds are often obtained using the aprotic solvents dimethyl sulfoxide DMSO and acetonitrile ACN. DMSO is widely used as an alternative to water because it has a lower dielectric constant than water and is less polar, and so dissolves nonpolar, hydrophobic substances more easily. It has a measurable pK range of about 1 to 30. Acetonitrile is less basic than DMSO, and so in general, acids are weaker and bases are stronger in this solvent. Some pK values at 25 deg C for acetonitrile ACN and dimethyl sulfoxide DMSO are shown in the following tables. Values for water are included for comparison. Ionization of acids is less in an acidic solvent than in water. For example, hydrogen chloride is a weak acid when dissolved in acetic acid. This is because acetic acid is a much weaker base than water. HCl plus C8 3C aqua H equals Cl plus C8 3COH plus 2. Acid plus base equals conjugate base plus conjugate acid. Compare this reaction with what happens when acetic acid is dissolved in the more acidic solvent pure sulfuric acid. H2S offer plus C8 3C aqua H equals HSO4 plus C8 3COH plus 2. The unlikely geminal diol species C8 3COH plus 2 is stable in these environments. For aqueous solutions, the pH scale is the most convenient acidity function. Other acidity functions have been proposed for non-aqueous media, the most notable being the Hammett acidity function, H0, for superacid media and its modified version H for superbasic media. In aprotic solvents, oligomers, such as the well-known acetic acid dimer, may be formed by hydrogen bonding. An acid may also form hydrogen bonds to its conjugate base. This process, known as homoconjugation, has the effect of enhancing the acidity of acids, lowering their effective pKa values, by stabilizing the conjugate base. Homoconjugation enhances the proton-donating power of toluenesulfonic acid in acetonitrile solution by a factor of nearly 800. In aqueous solutions, homoconjugation does not occur because water forms stronger hydrogen bonds to the conjugate base than does the acid. Mixed solvents. When a compound has limited solubility in water, it is common practice in the pharmaceutical industry, for example, to determine pKa values in a solvent, mixtures such as water/dioxane or water/methanol, in which the compound is more soluble. In the example shown at the right, the pKa value rises steeply with increasing percentage of dioxane as the dielectric constant of the mixture is decreasing. A pKa value obtained in a mixed solvent cannot be used directly for aqueous solutions. The reason for this is that when the solvent is in its standard state, its activity is defined as 1. For example, the standard state of water, dioxane mixture with 9:1 mixing ratio is precisely that solvent mixture, with no added solutes. To obtain the pKa value for use with aqueous solutions, it has to be extrapolated to zero co-solvent concentration from values obtained from various co-solvent mixtures. These facts are obscured by the omission of the solvent from the expression that is normally used to define pKa, but pKa values obtained in a given mixed solvent can be compared to each other, giving relative acid strengths. The same is true of pKa values obtained in a particular non-aqueous solvent such as DMSO. A universal, solvent-independent scale for acid dissociation constants has not been developed, since there is no known way to compare the standard states of two different solvents. Factors that affect pKa values. Pauling's second rule is that the value of the first pKa for acids of the formula XOM depends primarily on the number of oxo groups M and is approximately independent of the number of hydroxy groups N and also of the central atom X. Approximate values of pKa are 8 for M equals 0, 2 for M equals 1, 3 for M equals 2. Alternatively, various numerical formulas have been proposed, including pKa equals 8,5M, known as Bell's rule, pKa equals 7,5M, or pKa equals 9,7M. The dependence on M correlates with the oxidation state of the central atom X. The higher the oxidation state, the stronger the oxyacid. For example, pKa for HClO is 7.2, for HClO2 is 2.0, for HClO3 is 1, and HCl offer is a strong acid pKa 0. The increased acidity on adding an oxo group is due to stabilization of the conjugate base by delocalization of its negative charge over an additional oxygen atom. This rule can help assign molecular structure. For example, phosphorus acid H3PO3 has a pKa near 2, which suggested that the structure is H2H2, as later confirmed by NMR spectroscopy, and not POH3, which would be expected to have a pKa near 8. With organic acids, inductive effects and mesomeric effects affect the pKa values. A simple example is provided by the effect of replacing the hydrogen atoms in acetic acid by the more electronegative chlorine atom. The electron withdrawing effect of the substituent makes ionization easier, so successive pK values decrease in the series 4.7, 2.8, 1.4, and 0.7 when 0, 1, 2, or 3 chlorine atoms are present. The Hammett equation provides a general expression for the effect of substituents. Log K equals log K0 plus Rs. K is the dissociation constant of a substituted compound. K0 is the dissociation constant when the substituent is hydrogen. R is a property of the unsubstituted compound, and S has a particular value for each substituent. A plot of log K against S is a straight line with intercept log K0 and slope R. This is an example of a linear free energy relationship, as log K is proportional to the standard free energy change. Hammett originally formulated the relationship with data from benzoic acid with different substituents in the ortho and para positions. Some numerical values are in Hammett equation. This and other studies allowed substituents to be ordered according to their electron withdrawing or electron releasing power, and to distinguish between inductive and mesomeric effects. Alcohols do not normally behave as acids in water, but the presence of a double bond adjacent to the OH group can substantially decrease the pK by the mechanism of keto-enol tautomerism. Ascorbic acid is an example of this effect. The diketone 24, pentane-diene-acetylacetone, is also a weak acid because of the keto-enol equilibrium. In aromatic compounds, such as phenol, which have an OH substituent, conjugation with the aromatic ring as a whole greatly increases the stability of the deprotonated form. Structural effects can also be important. The difference between fumaric acid and malic acid is a classic example. Fumaric acid is M-14 but -2-enedioic acid, a trans isomer, whereas malic acid is the corresponding cis isomer, i.e. Z-14 but -2-enedioic acid C-cis trans isomerism. Fumaric acid has pK values of approximately 3.0 and 4.5. By contrast, malic acid has pK values of approximately 1.5 and 6.5. The reason for this large difference is that when one proton is removed from the cis isomer malic acid, a strong intramolecular hydrogen bond is formed with the nearby remaining carboxyl group. This favors the formation of the malate H+, and it opposes the removal of the second proton from that species. In the trans isomer, the two carboxyl groups are always far apart, so hydrogen bonding is not observed. Proton sponge 18-bistymethylamininophthalene has a pK value of 12.1. It is one of the strongest amine bases known. The high basicity is attributed to the relief of strain upon protonation and strong internal hydrogen bonding. Effects of the solvent and solvation should be mentioned also in this section. It turns out these influences are more subtle than that of a dielectric medium mentioned above. For example, the expected bielectronic effects of methyl substituents and observed in gas phase order of basicity of methylamines, meth3 and metwo-NHMe and H2 and H3 is changed by water to metwo-NHMe and H2 meth3 and NH3. Neutral methylamine molecules are hydrogen bonded to water molecules mainly through one acceptor, NHO interaction, and only occasionally just one more donor bond, NHOH2. Hence, methylamines are stabilized to about the same extent by hydration, regardless of the number of methyl groups. In stark contrast, corresponding methylammonium cations always utilize all the available protons for donor NHOH2 bonding. Relative stabilization of methylammonium ions thus decreases with the number of methyl groups, explaining the order of water basicity of methylamines. Thermodynamics, dynamics. Experimental determination. The experimental determination of pK values is commonly performed by means of titrations in a medium of high ionic strength and at constant temperature. A typical procedure would be as follows. A solution of the compound in the medium is acidified with a strong acid to the point where the compound is fully protonated. The solution is then titrated with a strong base until all the protons have been removed. At each point in the titration, pH is measured using a glass electrode and a pH meter. The equilibrium constants are found by fitting calculated pH values to the observed values using the method of least squares. The total volume of added strong base should be small compared to the initial volume of titrans solution in order to keep the ionic strength nearly constant. This will ensure that pK remains invariant during the titration. A calculated titration curve for oxalic acid is shown at the right. Oxalic acid has pK values of 1.27 and 4.27. Therefore, the buffer regions will be centered at about pH 1.3 and pH 4.3. The buffer regions carry the information necessary to get the pK values as the concentrations of acid and conjugate base change along a buffer region. Between the two buffer regions there is an endpoint, or equivalence point, at about pH 3. This endpoint is not sharp and is typical of a diprotic acid whose buffer regions overlap by a small amount. pK is about 3 in this example. If the difference in pK values were about 2 or less, the endpoint would not be noticeable. The second endpoint begins at about pH 6.3 and is sharp. This indicates that all the protons have been removed. When this is so, the solution is not buffered, and the pH rises steeply on addition of a small amount of strong base. However, the pH does not continue to rise indefinitely. A new buffer region begins at about pH 11 pKw3, which is where self-ionization of water becomes important. It is very difficult to measure pH values of less than 2 in aqueous solution with a glass electrode because the Nernst equation breaks down at such low pH values. To determine pK values of less than about 2 or more than about 11, spectrophotometric or NMR measurements may be used instead of, or combined with, pH measurements. When the glass electrode cannot be employed, as with non-aqueous solutions, spectrophotometric methods are frequently used. These may involve absorbance or fluorescence measurements. In both cases, the measured quantity is assumed to be proportional to the sum of contributions from each photoactive species. With absorbance measurements, the Beer-Lambert law is assumed to apply. Isothermal titration calorimetry (ITC) may be used to determine both a pK value and the corresponding standard enthalpy for acid dissociation. Software to perform the calculations is supplied by the instrument manufacturers for simple systems. Aqueous solutions with normal water cannot be used for 1H NMR measurements, but heavy water D2O must be used instead. 13C NMR data, however, can be used with normal water, and 1H NMR spectra can be used with non-aqueous media. The quantities measured with NMR are time-averaged chemical shifts, as proton exchange is fast on the NMR time scale. Other chemical shifts, such as those of 31P, can be measured. Microconstants. Applications and significance. A knowledge of pK values is important for the quantitative treatment of systems involving acid-base equilibria in solution. Many applications exist in biochemistry. For example, the pK values of proteins and amino acid side chains are of major importance for the activity of enzymes and the stability of proteins. Protein pK values cannot always be measured directly, but may be calculated using theoretical methods. Buffer solutions are used extensively to provide solutions at or near the physiological pH for the study of biochemical reactions. The design of these solutions depends on a knowledge of the pK values of their components. Important buffer solutions include MOPS, which provides a solution with pH 7.2, and tricine, which is used in gel electrophoresis. Buffering is an essential part of acid-base physiology, including acid-base homeostases, and is key to understanding disorders such as acid-base disorder. The isoelectric point of a given molecule is a function of its pK values, so different molecules have different isoelectric point. This permits a technique called isoelectric focusing, which is used for separation of proteins by 2D gel polyacrylamide gel electrophoresis. Buffer solutions also play a key role in analytical chemistry. They are used whenever there is a need to fix the pH of a solution at a particular value. Compared with an aqueous solution, the pH of a buffer solution is relatively insensitive to the addition of a small amount of strong acid or strong base. The buffer capacity of a simple buffer solution is largest when pH equals pKa. In acid-base extraction, the efficiency of extraction of a compound into an organic phase, such as an ether, can be optimized by adjusting the pH of the aqueous phase using an appropriate buffer. At the optimum pH, the concentration of the electrically neutral species is maximized. Such a species is more soluble in organic solvents, having a low dielectric constant. This technique is used for the purification of weak acids and bases. A pH indicator is a weak acid or weak base that changes color in the transition pH range, which is approximately pKa plus 1. The design of a universal indicator requires a mixture of indicators whose adjacent pKa values differ by about 2, so that their transition pH ranges just overlap. In pharmacology, ionization of a compound alters its physical behavior, and macro properties such as solubility and lipophilicity, log P. For example, ionization of any compound will increase the solubility in water, but decrease the lipophilicity. This is exploited in drug development to increase the concentration of a compound in the blood by adjusting the pKa of an ionizable group. Knowledge of pKa values is important for the understanding of coordination complexes, which are formed by the interaction of a metal ion, Mn+, acting as a Lewis acid, with a ligand L acting as a Lewis base, Lewis base, Lewis base, Lewis base, Lewis base, Lewis base. However, the ligand may also undergo protonation reactions, so the formation of a complex in aqueous solution could be represented symbolically by the reaction MH2 on M plus LH equals MH2 on 1 LM1 plus H3O plus to determine the equilibrium constant for this reaction, in which the ligand loses a proton. The pKa of the protonated ligand must be known. In practice, the ligand may be polyprotic. For example, EDT-Fer can accept 4 protons. In that case, all pKa values must be known. In addition, the metal ion is subject to hydrolysis, that is, it behaves as a weak acid, so the pK values for the hydrolysis reactions must also be known. Assessing the hazard associated with an acid or base may require a knowledge of pKa values. For example, hydrogen cyanide is a very toxic gas because the cyanide ion inhibits the iron-containing enzyme cytochrome C oxidase. Hydrogen cyanide is a weak acid in aqueous solution with a pKa of about 9. In strongly alkaline solutions, above pH 11, say, it follows that sodium cyanide is fully dissociated, so the hazard due to the hydrogen cyanide gas is much reduced. An acidic solution, on the other hand, is very hazardous because all the cyanide is in its acid form. Ingestion of cyanide by mouth is potentially fatal, independently of pH, because of the reaction with cytochrome C oxidase. In environmental science, acid-base equilibria are important for lakes and rivers, for example. Humic acids are important components of natural waters. Another example occurs in chemical oceanography. In order to quantify the solubility of iron Roman 3 in seawater at various salinities, the pKa values for the formation of the iron Roman 3 hydrolysis products FeOH2+, FeOH plus 2, and FeOH3 were determined, along with the solubility product of iron hydroxide. Values for common substances. There are multiple techniques to determine the pKa of a chemical, leading to some discrepancies between different sources. Well-measured values are typically within 0.1 units of each other. Data presented here were taken at 25 deg C in water. More values can be found in the thermodynamics section above. A table of pKa of carbon acids, measured in DMSO, can be found on the page on carbanions.